Hello students, in this lecture we are going to look at a very fascinating topic called virtual memory. So to understand the motivation for virtual memory, let's look at some scenarios which in the current day programming we don't even think about. So let's say as a programmers we are told that the maximum size your program can take is 1 GB or 2 GB or maybe 4 GB. It is limited by the main memory size of your laptop or desktop. If you are told don't write any program which is bigger than your main memory, how would you manage it? So some 20-30 years back, the programmers used to take up on this task by themselves, but we have a very sophisticated technique for this. So it's the current status is such that when we compile a program, the compiler assumes that the program can practically take an infinite addresses for itself, both for the instructions and for the data. There is no limitation on the program's possible addresses. It's called program's address space. Second scenario is where you are constrained that at any given moment you can run only one program on your system. Why? Because you can store or place only one program in the main memory at any given moment. It's even hard to imagine such a highly constrained situation, right? We have gone past it. So what it inherently says is the available main memory cannot be shared by multiple programs. Now if you ask why the scenario 2 would arise, is if we assume that all the programs are starting with an address 0 and go to addresses, let's say 1000 bytes, for example. If we have two programs, both of which have the starting address as 0, now how can we load address 0 of program 1 and address 0 of program 2 in the main memory at the same time? So because of that tricky situation, we are bound to load only one program at a time, either program 1 or program 2. Third scenario is somehow if we figured out to have more than one program in the main memory at a time, how can we stop one program from accessing the data of another program? It's concerning the safety and security of the data of one program. How can we or the OS restrict one program from accessing another program's address space? Also, at the other end, if I want to share the same data to multiple programs, more than one program, how can we do it? As you can see, we don't even think about these issues in our day-to-day life. And the remarkable concept that made this possible is virtual memory. It basically implements translation of program address to the physical address. Whatever main memory we were referring to is actually the physical memory. The program memory can be as large as it can be, but the physical memory is what we have in our laptops or desktops or even mobile phones. The translation done by the virtual memory can also help us to protect the data access of different programs. Also, it answers if you want to share the same data across multiple programs. At the same time, if because of this translation of addresses, many programs can simultaneously reside in the main memory. Basically, even if we have large programs, parts of those programs can reside in the main memory. How is this possible? Again, the working of virtual memory is very similar to the caches that we have seen over the past few lectures. We will place only the currently accessed data of the program. Here the data means both the instructions and the data of the program in the limited memory space that we have. Even though the program can be few hundreds of GB in size, at any given moment only some part of it will be active. That's the principle of locality for us. And if we make sure that this limited active portion is residing in the main memory, then we are good. The entire program resides in our hard disk or the solid state disk anyway. On demand, we are going to bring the requested data from the secondary memory to the main memory. Just like we are bringing the data from L2 to L1 if it was a miss in L1. The same way we are bringing the data from the secondary memory to the main memory if the processor has requested for it. So in a way, our main memory is acting like a cache for the secondary memory. Virtual memory controls the working of both the memory levels, the main memory and the secondary memory. To understand virtual memory, there are few new terms. The first one is a page. It is basically a virtual memory block. It is similar to the cache block that we have seen in caches. The size of this page is fixed, but if we want to go for variable size chunks, which are also called segments, the process followed is called segmentation. We are not going to touch upon that in this course. It will be covered for you in the operating system course in the next semester. Now with this fixed page size, we have two pages. One is the virtual page where the program's address space is divided into multiple virtual pages. And we have physical page where our actual physical DRAM is interpreted as a collection of pages. A page fault is an event where we are not able to find the virtual page in the physical memory. It's similar to a cache miss. The address that is typically generated by the processor is virtual address. Now when we say the address generated by the processor, it can be the instruction of an address which is generated at the fetch stage, or the address of a data which is generated in the memory access stage. Overall, processor works only with the virtual address. Virtual memory now translates this virtual address to the physical address. Address mapping or address translation handles both conversion of virtual address to physical address, also conversion of physical address to the virtual address. Now, if we want to enable sharing at a page level, then two virtual pages can be mapped to the same physical page. In that case, if, if the two virtual pages are belonging to different programs, they are actually using the same data because the physical page address is same. Now, how does virtual memory work? As already mentioned, the address translation is the key job that it performs. So, an high level view of what's happening, we have the virtual address, which is here in this example 48-bit long, 0 to 47, which is translated into a 40-bit physical address, 0 to 39. Here we find a page offset, which is again determined by the page size, similar to the block offset, which was determined by the block size in the caches. In this example, the page offset is 12-bit long. It means that our page size is 4 kilobytes. So in the virtual address, if we remove the page offset, whatever is remaining is called virtual page number. Similarly, in the physical address, what if we remove the page offset, we'll get physical page number. The translation happens between the virtual page number and the physical page number. The page offset is carried forward. Now, in this example itself, we can see that multiple virtual pages are mapped to few physical pages. Typically, the RISC-V ISA that we have been studying so far supports multiple virtual address sizes. Of course, we need to build the hardware for one such size. It can be 39-bit or 48-bit, 57-bit or 64-bit. The example we saw here is 48-bit virtual address. The physical address, if you observe, is 40-bit long. It means that our physical memory that can be supported by the RISC-V ISA is 2 power 40 bytes, which is quite huge. Now, why would such an address translation work, wherein we are trying to map multiple virtual pages to few physical pages? As you would have already guessed, we are going to place only the currently used virtual pages in the limited physical pages. It's predominantly because of principle of locality. So one design question is, how do we decide the page size? Just like we have seen this design choice or studied this design choice in caches, if we consider too small page offset, then we might not be able to capture enough spatial locality. But on the other hand, if we go for too big pages, the main memory will be filled with fewer pages. So it can trigger many conflict misses. So we need to be judicious in selection of the page size. Now, when a page fault occurs, we need to access the secondary memory. It's quite costly on both latency and power wise. Latency wise, because finding the page and transfer of the page from the secondary memory to the primary memory is very slow. It takes tens of microseconds. That means in terms of processor cycles, it might be millions of cycles. So we need to be very careful in handling the pages at the main memory. Also, whenever we are trying to access the secondary memory, whether it is a hard disk or solid state disk, there is significant power consumption. So it's always better to limit the number of accesses to the disk. Typical page sizes that we have are 1 kilobyte for embedded systems, somewhere between 4 kilobyte to 64 kilobyte for our regular desktop servers or workstations. Of course, there are few database implementations where the page size can be quite huge, but they are tailor made there. To reduce the page faults as much as possible, a fully associative mapping between the virtual address space and the limited physical space is used. As you know, fully associative mapping has zero conflict misses. All it has is capacity miss. So we have eliminated one type of misses already. What a fully associative mapping implies is during the address translation, any virtual page can be placed in any of the physical pages in the main memory. Also, let's assume that we have brought in a page from the secondary memory to the primary memory, and eventually we we evicted it from the main memory. Now, when there is a second request for the same page, when we are bringing again from the secondary memory to the main memory, the physical location or the physical page number can be different. That's what the fully associative mapping would mean. So it gives us extreme levels of flexibility to organize pages. But again, fully associative mapping, as you are aware, at the caches at least, we saw that it was power hungry and penalizing on latency front. But when we are talking at main memory, because we are dealing with latencies of tens of microseconds on a page fault, we can afford few extra cycles for a fully associative mapping. Also, we can afford extra power because it might be less than the power we need to access the secondary memory. Page faults are typically handled by the OS, mainly because the overhead of the software is less when compared to the implementation at the hardware. Also, the overhead of the software is much less when compared to the access time of the secondary memory. At the software, we can have much more flexibility with by exploring different types of algorithms, so on and so forth. Also, the notion of write through at the main memory doesn't make much sense, because whenever we are trying to write data to the main memory, it will actually come from one of the caches. If we end up making those writes visible to the secondary memory because of write through, then there will be way too many writes to the secondary memory. It's not necessary. Also, it's very penalizing in terms of latency and power, so it is never used. Write back is the only option at the main memory level. What it means is only when the page is selected as a victim candidate and evicted from the main memory, it will be updated at the secondary memory. So let's try to understand the working of virtual memory with the basic questions, 4 questions that we saw at the cache. The first 2 questions were how to place a block of data in the cache and how to find a block of data in the cache. At the virtual memory, the questions would be how to place a page of data in the cache and how to find it. As I already explained, we go for a fully associative mapping between the virtual memory and physical memory. It means that a physical page of the program can be placed anywhere in the main memory. Now, how do we realize such a fully associative mapping? Let's If you want to do a full search of all the physical pages that are currently in the main memory, it is very costly and time taking and also impractical too. For example, if we take effort GB main memory that we have, and if we consider a page size of 4 kilobyte, it can have 10 power 6 different pages. Now every time there is an access to the main memory, if we want to gloss over all the 10 power 6 pages, it's quite impractical. So what the designers have come up with is a small lookup table, which is specifically here called page table. A page table is indexed using the virtual page number, and it gives the physical page number if the mapping exists. If the mapping doesn't exist, then we need to go to the secondary memory. It is a page fault. Now every program has its own page table with its own virtual page to the physical page mappings. Now if you consider the scenario where multiple programs are using the same main memory, one program can have maybe 10 pages in its page table. Some other program can have, let's say, 12 pages active, and some other program can have, let's say, 20 pages. If we consider a main memory of, let's say, capacity of 50 pages, all the three programs can be supported by a single main memory. Now where is this page table located physically? It is stored in the main memory itself. Now if it is stored in the main memory, how will I know its location? We have a special purpose register, again just like a PC, which is not visible to the programmer, it's only visible to the OS. Here we have page table register, PTR. Each program will have its own PTR that will help to find out the exact location of the page table. Once we know the exact location, we can index that page table using the virtual page number. Now let's try to quickly walk through the entire process. The address generated by the processor is the virtual address, which is split into two fields. One is the page offset, other is virtual page number. We have the page table register, which stores the starting address of the page table. Using this, we will be able to locate the page table in the main memory. Page table typically has entries, something like this. Each entry is called page table entry, PTE, and it has the physical page address. Along with it, we have some status bits like valid bit, dirty bit, or few other extra bits for sharing, etc. Now the page table is collection of such entries. Now when a request comes to the main memory, the virtual page number is added to the address in the page table register. With that, we can index into the page table. If the valid bit is set, it means that the page exists in the main memory. The physical page number is taken from the page table. To that, we concatenate our page offset. This gives us our actual physical address to access the DRAM. The additional bits that can be in a page table entry, like I already mentioned, can be a valid bit or a dirty bit, which signifies whether there is some modified block of data in this page, so that when we have evicted, we will update the secondary memory also. A valid bit says whether the entry in the page table is valid or not. And there can be some dedicated sharing status bits. If it is set, it means that this particular page can be shared by some other program or some other process. There can be few other control bits that depends on the implementation. Now a quick question here. When there is, for example, let's say we have 3 levels of cache, and a lookup, we got a request from the processor for some address which resulted in miss in L1. So we looked up the L2. Let's say it's a miss there. Again we looked up the L3. Again it's a miss. So we come to the main memory. With the current page table implementation, the question is how many accesses to the main memory are needed to fetch this data. One access we will do for the page table. We use the requested address and the page table register value to get the actual page table entry. From that we get the physical address. To that we append the page offset. Again we access the page the main memory to get the actual data. So we are accessing the main memory twice. It means the miss penalty of L3 is twice the latency of the main memory, which is quite huge. But again, there is a very intuitive and interesting optimizations that the designers have come up for this problem. We will look at it in the coming classes. Let's try to understand the virtual memory completely. The third question is what happens on a page fault? When a page fault occurs, as I already mentioned, the OS takes control. How does it take control? The processor sees an exception which will trigger the OS using an interrupt service routine, specifically to handle the page faults. The OS takes control using the interrupt service routine. Whenever we are trying to load a program for this from the secondary memory to the primary memory, the OS actually creates a map of all the addresses of this program in the hard disk in a location called swap space. Now when a page fault occurs, we actually take the address and contact the hard disk. We at that point we use the swap space, we index into the swap space and get the actual location in the hard disk. Once we get the actual location, now we need to copy the data from the secondary memory to the main memory. Because it's huge, typically 4 kilobyte, the transferring of this data itself takes a lot of time. So the processor cannot do this. It will offload this process of transfer to a specialized hardware called direct memory access. We are not going to dwell into DMA right now. We are going to touch upon it in the IO module. DMA helps us to control the data flow between all the IO devices from the hard disk to the main memory. Now, upon a page fault, when we looked up to the main memory, if it is full, then similar to the caches, we need to select a victim candidate. Now we are going for a fully associative cache and we need to employ some replacement algorithm to pick a victim candidate and a victim, evict the page. The OS can deploy some sophisticated algorithms to decide the victim candidate. Unlike at the hardware, we were limited to LRU or FIFO or random or few other variants of it. Here the OS, because it has the control, we can go for some more intelligent algorithms. In RISC-V, an additional bit of information is stored which can be called as a reference bit or access bit or usage bit. Basically, it will help us to implement LRU algorithm. So in a way, if we look at the page fault, both the operating system and hardware have role to play. This was not the case in the caches because all the cache misses were handled by the cache controller itself. With that, I'll pause for today. We will have one more lecture in the virtual memory. After that, we are going to look at the actual DRAM. I'll pause for now. Thank you.